The standout example is the Changi-Guquan link, which came online in 2019. It currently holds the record for the world's longest power transmission line of its kind, spanning over 3,300 kilometers. It's also the highest voltage at 1,100 kilovolts compared to the 800 kilovolts of China's other UHVDC. It transmits up to a massive 12 gigawatts of electricity, which, for comparison, is almost as much as the average demand of Sweden's entire electricity grid in one single transmission line. There are another 8,000 kilometers of UHVDC under construction in China.
Picture a wire that starts in the deserts of western China and ends nearly 2,000 miles away on the eastern coast, carrying enough electricity to power tens of millions of homes, running at a voltage so high that no other country on Earth has ever safely operated one like it. That wire already exists. It's been running since 2019, and it's still the only one of its kind anywhere on the planet. This isn't a concept line or a pilot project waiting for funding. It's a fully operational piece of infrastructure that quietly answers one of the hardest problems in modern energy. How do you move enormous amounts of electricity across a continent-sized country without losing most of it to heat along the way? By the end of this video, you'll understand exactly how this line works, why the eye-popping speed number attached to it needs a bit of a fact check, and why the real story here, a country building a genuinely unmatched power grid, is more impressive than the viral headline anyway. Before we get into it, if you're into stories about the infrastructure nobody talks about that quietly decides who controls the future, subscribing means you won't miss the next one. Let's get into it. For most of the last 100 years, every country on Earth has run into the same basic wall when it comes to electricity. Power plants are rarely built where people actually live. Hydropower needs mountains and rivers. Coal plants need coal. And solar and wind farms need open land and consistent weather, none of which lines up neatly with dense cities hundreds or thousands of kilometers away. The further electricity has to travel down a standard transmission line, the more of it gets lost as heat, the same way a hose loses water pressure the longer and thinner it gets. The industry standard answer for decades was simple: keep voltages moderate, keep power plants relatively close to demand centers, and accept the losses as a cost of doing business. In the United States, the highest voltage in common use across the grid is 765 kilovolts of alternating current, a level largely unchanged for decades. The country's most significant direct current line, the Pacific DC Intertie connecting Oregon and California, runs at 500 kilovolts and has been in continuous service for more than 50 years. It works, but it was never designed to move power across a landmass the size of an entire continent efficiently. The assumption baked into nearly every national grid on Earth was that you build generation near demand, and long-distance transmission stays a secondary, lower voltage affair. Fast forward to now, and that assumption still holds almost everywhere outside China. America's grid remains fundamentally an alternating current system capped at 765 kilovolts, and the country doesn't operate a single ultra-high voltage direct current line at all. Its handful of HVDC links add up to only a few gigawatts of total capacity nationwide. Texas only approved its first 765 kilovolt lines in 2025, treated as a major regional upgrade rather than a routine addition. Japan built a 1,000 kilovolt AC demonstration line decades ago, but never actually ran it at that voltage. The old Soviet Union built roughly 2,362 kilometers of 1,150 kilovolt AC circuits, but most of that network now runs at reduced voltage. Brazil and India have each built impressive 800 kilovolt direct current lines to move hydropower and coal-fired electricity over long distances. India's Northeast Agra line stretches 1,728 kilometers, and Brazil's Belo Monte project moves power roughly 2,000 kilometers from the Amazon to Sao Paulo. Both are genuinely serious pieces of engineering, but none of them cross the line into what engineers actually classify as ultra-high voltage direct current at the very top tier. As of today, nobody outside China operates a commercial direct current line above 800 kilovolts. That threshold, the one separating very good grid from in a category of its own, belongs to exactly one country. China, by contrast, has already built at least 23 separate plus or minus 800 kilovolt UHVDC lines of its own. On top of pioneering the world's first multi-terminal converter grid at Jiangbei, meaning even China's second tier of transmission technology, is already running at a scale most other countries would. Consider a flagship national project. Part of the gap isn't purely technical, it's structural. In the United States, a transmission line that crosses state lines, say from Iowa into Illinois, has to navigate separate regulatory proceedings, different regional grid operators, competing cost allocation fights, and state authorities that can effectively veto a route they don't like. Federal reforms aimed at streamlining that process face years of legal challenges before they change anything on the ground. When a Chinese UHV project crosses 5 provinces, as several of them do, the central government sets the route and the state utility executes it. Provinces can negotiate over compensation, but they can't block the line outright. That's not a technology gap. It's a decision-making gap, and it's arguably the bigger reason China's grid has pulled so far ahead. That line is called Changji Guquan, and the numbers attached to it are the kind that don't have a real peer to compare against. It runs 3,293 kilometers, roughly the distance between Los Angeles and Cleveland, starting in Xinjiang in China's far west, where enormous wind and solar farms generate more power than the region can use, and ending in Anhui province in the industrial east, where the demand actually lives. It operates at plus or minus 1,100 kilovolts of direct current, the highest voltage any commercial power line has ever run at anywhere in the world. Its capacity is 12 million kilowatts, enough to meet the annual electricity needs of roughly 50 million homes from a single transmission corridor. State Grid Corporation of China, the state-owned utility that built it, nicknamed the project the Power Silk Road. It was approved in December 2015, broke ground the following month, and was fully operational by 2019, at a cost of roughly 40.7 billion yuan, close to $6 billion. And it isn't an isolated flagship project built for headlines. It's one node in a network of 19 ultra-high voltage AC lines and 20 ultra-high voltage DC lines that together stretch more than 40,000 kilometers across China, forming the backbone of the country's decade-spanning strategy to move power from its resource-rich west to its population-dense east. So, how do you actually push electricity at a voltage nearly 40% higher than anything else running commercially on Earth without the whole system arcing apart? The honest answer is that going from 800 kilovolts to 1,100 kilovolts isn't a small step up. Engineers who've worked on these projects describe it as a far bigger technical leap than going from 500 to 800 kilovolts, because insulation requirements don't scale in a straight line with voltage, they scale exponentially. Every piece of equipment along the route, insulators, transformers, the massive converter stations at each end, has to be re-engineered from the ground up rather than simply built bigger. Picture a single cable trying to carry that much current. It would need to be absurdly thick, and thick conductors radiate current unevenly, wasting power at the edges through a phenomenon called corona discharge. The engineering solution is to split the load across bundles of thinner conductors. Instead, the Changji Guquan line uses bundles of 8 separate wires per line, each roughly the thickness of a human wrist, working together instead of one massive single cable. It's the same logic as running 8 garden hoses side by side, instead of forcing all that water through one pipe wide enough to burst. At each end of the line sit converter stations, essentially massive electrical translators that switch power between alternating current, which is what most of the grid and most machinery uses, and direct current, which is what actually makes 3,000 plus kilometer transmission efficient in the first place. Direct current loses roughly half as much power over long distances as alternating current does, because AC's back and forth oscillation itself burns energy that DC simply doesn't waste. Push the voltage up to 1,100 kilovolts on top of that, and the efficiency gain compounds the line's transmission losses run at less than a quarter of what a standard 500 kilovolt line would lose carrying the same power the same distance, while needing a transmission corridor only about 55% as wide and costing roughly 40% less per unit of capacity delivered. Those converter stations aren't small pieces of equipment either. Building transformers capable of handling 1,100 kilovolts meant multinational suppliers who'd worked on China's earlier 800 kilovolt projects had to redesign and rebuild entire factory lines just to produce components large and heavy enough for this next jump, pieces of hardware so oversized that nothing at the previous voltage tier could simply be scaled up. They had to be engineered again almost from scratch. And because the towers carrying these lines run so high and so remote across mountainous terrain, routine maintenance increasingly relies on helicopter crews rather than technicians climbing the structures by hand, since the towers themselves are often too tall and the terrain too difficult for the traditional approach to be practical or safe at this scale. Here's why a single transmission line deserves this much attention. It's solving the exact geographic mismatch that limits how far any country can lean into renewable energy. China's wind and solar resources are concentrated in its western deserts and northern plains, while its factories, cities, and actual electricity demand sit 1,000 miles away on the coast. Without a way to move that power efficiently, all that renewable generation capacity sits stranded, curtailed, or simply wasted, which is exactly what was happening in Xinjiang before this line existed, with the region posting some of the worst curtailment rates in the entire country because there was nowhere for the extra power to go. Zoom out further, and this line is a single thread in something much bigger: Beijing's Global Energy Interconnection Initiative, a Xi Jinping-backed proposal first floated in 2015 to eventually link power grids across more than 80 countries into something resembling a planetary supergrid. One SGCC executive has reportedly described UHVDC technology as an intercontinental ballistic missile for the energy sector, a deliberately dramatic way of saying this isn't just about keeping the lights on. Domestically, it's about China positioning itself as the exporter of the technology and standards that the rest of the world's future grids might eventually run on, the same way it's positioned itself in solar panels, batteries, and EVs. There's an environmental angle here too that rarely makes it into the viral clips. The 12 million kilowatts flowing through this one line each year displaces the equivalent of tens of millions of tons of coal that would otherwise need to be burned closer to the cities actually using the power, cutting tens of millions of tons of carbon dioxide along with the sulfur dioxide and nitrogen oxides that come with coal combustion. China has also used its UHV build-out to justify banning new coal-fired plants across Xinjiang and roughly 20 other provinces, on the logic that if you can move clean power efficiently enough over long distances, you don't need to keep building fossil fuel plants next door to every city that needs electricity. Whether or not you buy China's broader climate record, that's a genuinely different way of thinking about the relationship between where energy gets made and where it gets used. If this sounds like a pattern you've heard before on this channel, that's because it is. China identifying an infrastructure category, deciding it's strategically important, and then out-investing and outbuilding every other country until it's operating in a class by itself that's the exact same story as solar panels, batteries, EVs, shipbuilding, and now humanoid robots. What's different here is that this isn't a consumer product competing for global market share. It's the electrical backbone underneath everything else China wants to build, including the factories manufacturing all those other products this channel keeps covering. A robot factory running 24 automated assembly stages, or a shipyard launching vessels around the clock, both eventually plug into the same grid this line feeds. Dominating the power infrastructure isn't just one more industry China happens to be winning, it's the foundation that makes winning the others logistically possible in the first place. The engineering achievement here is completely real and, frankly, underappreciated outside industry circles. Building the world's only commercial plus or minus 1,100 kilovolt line and running it successfully since 2019 is a genuine first, not an exaggeration dressed up for a headline. What bugs me a little is watching a legitimately record-setting piece of infrastructure get packaged with a speed statistic that doesn't survive basic arithmetic, because it means the real story voltage, scale, and strategic intent gets buried under a number that was never really about this specific line to begin with. I also think it's worth resisting the urge to treat this purely as a China wins again story without asking what it actually costs to build a grid this centralized. Part of why China can push a single line across 5 provinces without the years of jurisdictional fighting that plagues similar projects in the United States is that provincial governments don't get meaningful veto power over where these lines go. That's a real advantage for speed of execution, and it's also a real trade-off that a more federalized country would have to grapple with before trying to copy this model wholesale. So here's the question I keep turning over. Is a centralized, government-directed grid genuinely the only realistic way to build infrastructure at this scale and speed? Or is that just the easiest explanation for why everyone else's grid still looks the way it did 20 years ago? I'd honestly like to hear how you'd answer that, so drop your take in the comments. If you want to keep following how far this grid strategy actually extends, because 40,000 kilometers of UHV lines is still growing, subscribing means you'll catch the next chapter the moment it happens. And if this one caught your attention, we've got another story queued up about an industry where a single number completely rewrote what experts thought was possible for the next decade. You won't want to miss that one either. China Tech Frontier, where the numbers the headlines skip over get the full story.